set my alarm here. All right, so we're going to shift gears to another topic in medicinal plants and talk about infection. I know you were all waiting for this infection game. So in my lab, we work on medicinal plants that are used in indigenous medicine for infectious inflammatory skin disease. And today I'm going to show you a little bit about our work where we are using ethnobotany-directed bioassay-guided fractionation to identify molecules that can help us deal with the antibiotic crisis. So I'm going to go over the ethnobotanical approach to drug discovery, the post-antibiotic era. What does that mean? We're not even a full century into the antibiotic era. And how do we discover new chemistries, new biological activities that can be translated into pharmacologically relevant therapeutics in the future from medicinal plants. So this is just an overview of what our drug discovery approach is. So we're starting with ethnobotanical knowledge, either recorded in present-day ethnobotanical interviews, or we're going back to historic literature, or in some cases it's some of both. And we're looking for details like parts of the plants that are used, how they're extracted, how are they applied, because all of those different elements play a big part in the final chemical composition of each extract or formulation that we're testing. And that, of course, is relevant to the final pharmacological activity. We incorporate all these different steps along the way: botanical identification, collection of herbarium, voucher specimens, chemical characterization, biological assays, and so on. But something that I think is really important that sometimes we miss is that this is not a blinded approach. We're starting with therapies that have been used, especially for skin therapies. People can tell us what their boil looks like or what that infected burn wound looks like. We're looking at things that have been used for millennia in some cases to treat infection. And yet we still don't really understand how many of these work. But it is a very directed approach. We have around 391,000 species of plants, and about 7% of those, around 28,000 according to Q's most recent State of the World Plant Report, are reported as being medicinal. But if you look into the pharmacological literature that really goes into the in-depth evaluation of how many of these have actually been explored for their chemical makeup and for their full spectrum of biological activities, I would say we've barely scratched the surface, maybe a few hundred at the most. And so, I love to show this slide, especially to medical audiences, just to remind everyone that the very foundation of Western medicine is actually based in traditional medicine. These are all compounds that are listed on the World Health Organization's list of essential medicines. These are key medicines that are essential for every clinic to have for the treatment of pain, the treatment of cancer, and for the treatment of cardiac disease, and so on. These all came from plants. So this idea that going back to nature is strange or not the usual way of discovering drugs is absolutely not true. This is how we have always found the majority of our drugs in the past. So in my lab, we are working on a collection, or we've been building a collection of 600 species. We are focused on looking at plants that are used in the treatment of infectious inflammatory disease. We have collections spanning the US into China, North Africa, and especially the Mediterranean. These are all collected under appropriate agreements with different countries and through access and benefit sharing initiatives. Out of these, we have 1,900 extracts. And so what we're really trying to do is understand how are these working, especially in the treatment of infection. The problem that we face is actually a really critical problem. We're entering what's going to be known as the post-antibiotic era. Post-antibiotic era is a period where we don't have antibiotics that work as we're accustomed to having them work today. If you think about all the times that you've taken an antibiotic in your life, whether it be for an ear infection or for surgery or when you've had some dental work, imagine if those options were no longer present. Some recent evaluation of projected deaths and current deaths is that we know that today around 700,000 people die globally due to untreatable infections. And that roughly comes out to around 6 plane loads of people a day. if you're thinking of 300-seater flight, right? I have a hard time putting my head around numbers, so I'd like to use it in terms of plane loads. 30 years from now, that's going to be 4 plane loads an hour. So we have a very serious problem that we're trying to deal with. Part of this has been exacerbated by a massive gap in discovery for novel antibiotics. We haven't had a new antibiotic introduced, or just that's been introduced into the clinic since the 1980s was when the last new class was discovered. So we have this discovery void. And because of that discovery void, we're now starting to see more and more problems. A lot of the new antibiotics that have been introduced into the clinic are not actually new. They're what we call redo drugs. These are drugs that have been modified slightly in structure and then brought back out. And as someone that knows a bit about natural products chemistry, it's no surprise to me that this discovery void also coincides in a period in pharmaceutical discovery where they dropped off a lot of their natural product programs. And so they moved more towards synthetic chemistry and combinatorial chemistry libraries. So the bug I'm going to talk about today is Staph, or MRSA, methicillin-resistant Staph aureus. This is an organism that is responsible for a plethora of diseases, especially relevant to skin and soft tissue infections. It is the cause of many, many medical device infections, endocarditis, sepsis. You've probably heard about that in the news. And it's also the source of a bioterror threat. It has a toxin that is used as a bioterror threat. So one of the big problems with Staph is that even though we do have some drugs that work against it, it's still incredibly recalcitrant and can be very aggressive. And the way that Staph and other bacteria evade antibiotic activity, there are many different actual pathways that they can evade action. So today I'm only going to focus on the enzymatic degradation pathway, basically where they're able to produce enzymes that break apart the drugs that get into the cell and render them inactive. And so the class of antibiotics I've been interested in are the beta-lactam antibiotics. Many of you in this room have probably had a beta-lactam antibiotic at some point. The first ones were, of course, the penicillins. The way that these become inactivated is that bacteria release an enzyme that cleaves that red square ring that you see there. And so the goal is to come up with something that can prevent that process. And so what we did in this particular study is we took the library, we took a portion of the library, just around a little under half of our library, and screened it in combination with an antibiotic that otherwise doesn't work. So we took a quarter of the dose of the MIC and screened it in combination with our extracts. And through this process, it's an iterative process, we're looking for things that are synergistic, or things that make the antibiotic work again. And through this cyclic process, we are looking for, again, synergy. So if you have drug A and drug B together, neither one might work on their own, but together they really start to work very well. So we're looking for the synergy line in the isobutyrogram. And so we had some interesting success. So out of these 900 extracts, we found that we had a 3% hit rate. And one of the ones that really caught my attention was from a medicinal plant used in Native American medicine as a poultice for infected wounds and ulcers. So I get really interested in things that are applied topically to wounds and ulcers because people can see what's actually happening in the healing process. And what was really fascinating about this particular extract is even the crude extract could drop the MIC, or drop the dose required for activity of the antibiotic, by 1,000-fold. That's really impressive. You don't see that very often in these kinds of studies. And so one of the problems we run into, of course, is that crude extracts are very complex. Even partitions of extracts are very complex. So that's also part of the beauty of nature, right? Because sometimes it's multiple compounds working together to get the desired activity. But in the lab, we still have to work on separating these to better understand the roles of each of these compounds. And so we've innovated a lot of kind of hand-built, do-it-yourself equipment in my lab. This is one of our latest ones. This is a robot that my husband built actually out of Lego parts. He literally raided the Lego toy box at home, got some wood, ordered a mindstorm thing. So something on this scale would have cost us in the ballpark of $15,000 to $20,000. We got it for under 200 bucks. So I had to show that off. And because of this innovation, we've now had more and more success in isolating crystals of compounds from this plant. We are identifying those structures through NMR, mass spectrometry, and X-ray crystallography. So we're making progress in understanding what some of the responsible compounds are. And these are two fractions off of the ethyl acetate partition. And I just wanted to point out that as we are continuing in our isolation strategy, we are seeing greater and greater activity. And you can see in this plot, the dark shows heavy growth. And I wanted to point that out because neither of these drugs work well on their own. So in this case, you have the extract fraction, and on the other end going horizontal is the antibiotic. So where the dark colors are, that's showing heavy growth. So alone, they do not work. Together, they do. And you can see this very clearly with this isobologram showing that we've got really, really potent activity. And so what we're doing currently in our future directions, we're going to be looking more and more to try and understand which compounds are responsible. But I'm also very interested in understanding what is the relevance or what other compounds in the plant might also have some antibacterial properties. Because we're taking this and combining it with another existing antibiotic, there might be some other activities at play. There's still a lot to explore here. Moving forward, if this were to be developed as an adjuvant or an add-on to antibiotics, we would need to do additional studies with pharmacokinetics, pharmacodynamics, absorption studies, additional toxicity studies. The extract is non-toxic at this stage of development. And then move into in vivo studies to see how well this does in an actual living organism. And I think this study is a good example of some of the different benefits we get from working with medicinal plants. We know that botanicals that have been in use for a very long time have some promise, because otherwise people wouldn't be using them for so many years. We know that synergy may be at play, and there are pathways beyond the classic single compound isolation pathway, including the botanical drug pathway, that can be leveraged to advance these kinds of therapies. So I'm going to start by thanking my group and thanking one of our collaborators. The major players on this particular study are shown here, including Dr. Melander. And as another note, because we were speaking about podcasts the other day, I'm going to make a little pitch. I have a podcast on the food medicine continuum, so nothing to do with antibiotics at this point, but if you're interested in learning more about medicinal plants and foods, you can check that out. Thank you.